Hey gang, in this video we're going to discuss the idea of independent events and how that affects or does not affect probability. So independent, it has a pretty straightforward interpretation that I think translates into English pretty well. And that's when if something occurs, if one event occurs, it does not affect the probability of another event. Independent. And we've already seen some examples of independent events, but I've been withholding information from you. But we will do another example today without holding information from you. And let's consider classical coin flip, flipping a coin 3 times. And maybe I should say flipping a fair coin 3 times. Well, does the first flip, whatever you get, have any influence on a subsequent flip? No, right? And what you get on the third flip has no bearing on what came before it. So each flip would be considered an independent event because they are not influencing the probabilities across the flips. Cool. So I'm going to ask a little question here then, a little probability question. Let's find the probability of getting tails, 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 3 tails. Since it's a fair coin, we know that in one flip, getting a tails would be probability 1/2. And in the second flip, that probability does not change, 1/2. Third flip, 1/2 for tails. Now, how on earth are we going to combine these values? We're not going to add them. They would add to something more than 1. We would multiply them. So here, this is 1/2 raised to the 3rd power. I kind of like to write it like that, which is 1/8 or 0.125. Sweet. While we're working with this example, I want to show you a probability tree, which is a useful tool to organize all the possible events and outcomes in a scenario, such as flipping a coin 3 times. So I'll scroll down here because I'm going to need some more space. Sometimes these are drawn vertically, kind of like this, and there's like branches, but I kind of like to do these horizontally, and it really doesn't matter. For this scenario, what these little branches are representing are the possible outcomes in, say, the coin flip. This would represent the first coin flip. First flip. And I might write on the end of these branches the possible outcome from a single flip, which would be either heads or tails. And along the branch, I like to write the probability of each of those outcomes. I'm going to do 0.5 and 0.5. So this is the first flip, and we've got 2 more flips to go. So I'm going to write another set of branches extending off of this first branch. This is the second flip. And there are 2 possibilities for each of these branches. Either head or tail, head or tail. And because this is a fair coin, we know it's got a probability of 0.5 for either heads and tails. Sweet. And so we've got to draw this one more time. And it's going to basically just be a replication of what we see here, but it's going to keep extending out. So here we go. Okay, so I've got the first, second, and third flip illustrated, and essentially the way you sort of look at these trees are you kind of travel down the tree. So I'm going to maybe use yellow here to represent what it looks like when you get 3 tails, right? Because in our previous example, we said, what's the probability of tails, tails, tails? And we know that that was 0.125. So that is the first flip, you obtain a tails. The second flip, here's the options here. Now it's time for your second flip. Could be heads, it could be tails. If we're talking about tails, then I'll circle T. And here comes the third flip. We're talking tails. So you sort of travel along this tree and you gobble up these probabilities along the way, right? We said this was 0.5 cubed. If you wanted to consider the probability of 3 heads in a row, I'm going to delete my yellow here, make a trade for orange. The probability of 3 heads in a row, well, let's travel down the tree. That would be H, H, H. So you would gobble up 0.5, 0.5, 0.5 all the way down, and that would be the same answer as above, 0.125. So when flipping a fair coin 3 times, maybe you can see here that there's actually 8 events in the sample space, right? Each one of these traverses down the tree would be a different event. And maybe I can just write the whole sample space out, sort of a little lazy here, but this would be heads, 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 tails. This would be heads, tails, heads, and I'm still gonna keep going. Heads, tails, tails, heads, tails, tails. This one would be, all right, now I'm getting tails on the first flip. T, H, H, T, H, T, 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 H, and lastly, all tails. So since there are 8 outcomes in the sample space, and they all were developed by corresponding probabilities of 0.5 all along the way, they were all the same, don't all of these have probability of 0.5 cubed? Right? All of these must have probability 0.5 cubed. I do have another question I want to ask. This will sort of be a preview to an upcoming chapter. How many ways can you obtain 1 head in 3 flips? 1 head in 3 flips. Okay, well, let's kind of analyze this sample space. That has 3 heads. That has 2, 2. Ah, here's one. That has 2 heads. Oh, here's another one. And here's another one. The answer to this question is 3, right? There are 3 ways to get 1 head out of 3 flips, because that head can occur in the first flip, in the second flip, maybe I'll highlight those, or in the third flip. So maybe we can also ask another supplementary question here. What would be the probability of getting 1 head? Well, it's 3 out of these 8 ways, right? 3 out of 8. So I've introduced this probability tree, and we're thinking about independent events, hopefully, right? Each of these flips is considered independent. And there's a rule associated with independent events, and we've used it quite a bit already, but I haven't formalized it. So let's formalize the rule for probabilities associated with independent events. Some of these probability rules are not very creatively named, right? We had the addition rule. Here, this is the multiplication rule, in which if we have 2 events that are considered independent, then the probability of E, the first event, and then the second event, F, is simply the individual probabilities multiplied. So that's a really nice property because multiplication is pretty straightforward. Let's consider another example to illustrate some independent events and also bring in some other properties of probability. Scroll down here. Okay, I believe there's a question similar to this on the homework. Suppose a multiple choice exam has 5 questions. Each of them has 3 options. And what is the chance of getting all 5 questions correct by random guessing? Okay, well, on one of those questions, since there's 3 options, A, B, and C, wouldn't we presume that there's a 1 in 3 chance for getting 1 question correct? And assuming that each question is independent, we can then just multiply. Oh, well, the second question would also be 1/3. The third question, probability 1/3. And it is the idea or assumption of independent events that allows us to multiply the probabilities of the individual events like such. So this is 1 over 243, which is the probability of all 5 correct. Okay, so very important there is assuming that each question, each Q is independent. Next part, part B, what is the probability of getting at least 1 question wrong by guessing? So we have a couple different elements here. Now this is wrong and at least 1. Well, there's a couple ways to think about this. Because there's 5 questions, I don't really want to draw a big tree. It'll be really a lot of info to draw down. So I'm going to organize a little table here. I think it's kind of a nice way to organize some info, where I'm going to have the columns be the number of correct questions, the number of wrong questions, and the corresponding probabilities. we know that it is possible to get 0 questions correct, or 1, or 2, or 3, or 4, and since there's 5 questions on this exam, it's possible to get 5 correct. Which means that if there are 0 correct answers, then all 5 are wrong. If there was 1 correct answer, then 4 are wrong, and kind of just going on down here. And we already addressed one of these probabilities. We found the chance of getting all 5 questions correct, right? That was the 1 over 243, and all 5 questions correct, that would be this very last one. 1 over 243. And so there are actually 6 probabilities that would go into making this complete table, right? And all of those probabilities would have to add up to 1. That's a fundamental property of probabilities. And this question that is being asked here, what's the probability of getting at least 1 question wrong? If I was to circle those here, we want these probabilities at least 1 wrong. So that could be 1 wrong, or 2 wrong, or 3 or 4 or 5 wrong, but not 0 wrong. So we want all of these probabilities that we have not yet found, but we get to use a property that was introduced in a previous video. Can't we use the property of complements, where we want all of the probabilities except this one in brown, 1 over 243. So our answer here can be found by doing the probability of at least 1 wrong is given by 1 minus the probability of 0 being wrong. But we already know the probability of 0 wrong answers because that's the same as all 5 being correct. So 1 minus the probability of all 5 correct, which is 1 minus 1 over 243, which is, if I thought about the common denominator here, that would be a common denominator of 243, and that'd be 242 in the numerator, which is a pretty substantial probability. It's about 99%, 0.588. So in this question, not only did we use properties of independent events, but also complements. And complements can make a hard problem seem a lot easier, but you have to be able to identify it. Often when we have an at least 1 sort of question, at least 1, think about, well, do we have the answer for 0? Because if you do, at least 1, that's this red oblong oval here, at least 1 and 0 wrong are complements. So this red circle and 1 over 243 are complements. Hope you enjoyed that example. There's one like it on the homework. Have a good day.